People who are interested in finite elements get enthralled with the equations that describe the system, and since this is a large set of equations, typically 5 to 50,000 degrees of freedom, it seems to be a dominant aspect of the total picture. In fact, though, it's the modification of the equations prior to solution that's really important and where the real engineering comes in. So I've packaged together some of these methods and put them in a lecture called Modification of Equations. To some people this might seem a little strange as to why worry about this, but it is the real finite element theory that's exemplified by these methods. First we'll start with a description chronologically of the solution process. This leads to the creation of a standard form where all of the unknowns are on one side of the equation and the knowns are on the other. And then I go into a series of things that must be separately considered in the setting up of the finite element problem. And these are really important topics that distinguish between the casual user and the expert user. We'll have a problem session at the end. Let's now talk about the solution process, where we'll follow the logic that the finite element analyst might use. This could be a little different than the logic that a modeler might use working on a screen, or that a mathematician might use. I think I'd like to follow, indeed, the chronological order in which the finite element code itself will, in most codes, remove variables, clean up the problem, and organize it into the optimal form. Generally, we start with a set of equations shown at the top here in the linear static form. Many finite element laws are like this, even including frequency response in dynamics, where the stiffness matrix might be a function of a forcing frequency. But generally this is a set of linear equations, and we're interested in the static case. Now, what will happen first is that the multipoint constraints that have been imposed on the problem should be first carefully considered, and this generally removes a degree of freedom for every multipoint constraint. We'll talk about those in a few minutes. Then the single point constraints are removed. This will take a pretty big chunk out of the problem size. You might see on the right here I've shown, perhaps with a 50,000 degree of freedom problem, that you might remove only, say, 50 degrees of freedom due to multipoint constraints. On the other hand, it's quite common for 10% of the degrees of freedom to be removed by the single point constraint list. And these would be the normal boundary conditions where the body is being held fixed to the ground. Following that, it's still the analyst's obligation to remove any remaining rigid body modes. And these are the ones that would allow the body to move around in space and cause a singular stiffness matrix. That will, in general, remove as many as 6 more degrees of freedom, but not a big reduction. Then, having the equations in somewhat of a standard form here, notice that I have the red color here for the displacements that are unknown, and they are now organized on one side of the equation and the forces on the other. At this point, you worry about optimization and whether you need to resequence the degrees of freedom to minimize bandwidth or wavefront. Once that's done, you can then solve the problem, and although I show here a symbolic inversion, in fact the body, the stiffness is not really inverted, but rather is handled by what is called triangular factorization. So this is a nice symbolic way to think about solution, but in fact isn't done that way. Then, when the solution for displacements is finally found, you can then recover forces. You can recover forces of constraint, internal element forces, bending moments, this sort of thing, membrane stresses, interior stresses, strains, and any other detailed information. This recovery step need not be done, in fact, if it isn't necessary, but is in typical problems. Now let's concentrate on this standard form. The standard form has all the unknowns on one side of the equation and all the knowns on the other, as shown here. This desired form is one where the forces are known and then the unknown displacement, shown here in red to attract your attention, are all on the left. Now, furthermore, you would like for the ideal problem for the stiffness K to be real, symmetric, and positive definite. This will imply a stable structure that can give a response under a given loading condition. Now, unfortunately, the original statement of such a problem generally is not in this standard form, but rather is in a mixed boundary value form shown below. And this is where you have some of the displacements as unknowns, but some of the forces as unknowns. I show a non-homogeneous displacement condition here. That is a non-zero value of 4 units in the third displacement component. That means that the engineer doesn't know the reaction force over here, or a force of constraint that's imposing that displacement. And this problem in this mixed form is difficult to handle, so we have to straighten that out. I'll repeat the mixed boundary value problem that I had at the bottom of the previous figure here, so that we can refer to it when we look at our reduction method here. First of all, one of the most efficient ways to handle this problem is by partitioning. Interestingly, partitioning isn't discussed much in textbooks, and yet it's the way that you can remove those prescribed degrees of freedom and then efficiently solve the rest of the problem. I show that here where the third equation appears below, and once the 2x2 problem has been solved, then the solution for the reaction force, or so-called force of constraint, would be a forward multiplication leading in this direction to the force of constraint. In order to do this partitioning, though, you must account for the terms that have been removed of the form 1 times 4 in the first equation, which is shown subtracted off, and then 2 times 4 in the second equation, also subtracted off. So the penalty that you pay for partitioning is a certain amount of bookkeeping in keeping track of which degrees of freedom have been removed, and then a certain amount of updating of this vector on the right side. Notice that if it had been a homogeneous boundary condition, which is by far the most common, with a zero displacement imposed, then you don't get these correction terms because they drop out. They're identically zero. Now, for small computer programs, and you'll see this sometimes taught by teachers in college classes, that you would rather not go through the partitioning, because if the prescribed displacements are sprinkled throughout the structure, you get into Boolean algebra where you have to really bookkeep on which ones are now gone and which ones are remaining. A way around that would be to carry that equation where the displacement has been prescribed in a trivial way. So you carry along trivial equation, but doesn't require renumbering. In this case, you put a unit value in the coefficient matrix on the diagonal. You put zeros in the rows and columns that correspond to that dominant term, and then you put the enforced value on the right hand side. This also requires that you correct the load vector, and you get an apparent external load here due to that known degree of freedom in the remaining coordinates. Again, though, relatively easy to do for homogeneous displacement conditions where you force displacement to be zero, because then these would drop out again. The nice thing about this is then that you don't have to do the work of the Boolean algebra to keep track of your mapping of your old coordinate set and your new coordinate set and the relation between them. Rather, you solve again an n by n set of matrix equations here, whereas previously you had something less than that. There is another way to solve these equations in the original number so that you don't require renumbering your entire set of variables. This is called a penalty approach, and again you pretend that you don't know what this value of the enforced displacement was, and if its value was to have been 4, you put that over here in the load vector, you carry along the coefficient of that term on the main diagonal, which is good from a standpoint of scaling that we'll think about in a minute. And then you multiply that term by 10 to the 8th, both on the force over here and on the coefficient here. Now what you have just done is to put a rather large number here that will drive this supposedly unknown displacement, although we really know what it is, to take this value of 4. Because you see, if the 7 is scaled of roughly the same size as the other terms in the equation, and we do have pretty much diagonal dominant terms in the finite element method, then this 10 to the 8th will mean that we will overwhelm the other terms. The third equation will basically say that u3 equals 4. There will be some slight error in that, and it can be driven out by raising the exponent to higher and higher powers. This same method is used in linear programming. I know years ago I taught a method called the Big M method, and the Big M was a big multiplier. See, that multiplier is the punishing, it's the penalty that will not allow the known displacement u3 to vary much from its prescribed value. Lastly, one could use Lagrange multipliers in such an attempt to solve these equations. Again, you might pretend that you didn't know this displacement and leave the equation as it stands here. Then you would have to add an equation that would prescribe this condition, and with a Lagrange multiplier that would again penalize you if this were not true. And that Lagrange multiplier can take values which can have physical interpretation. But in any event, rather than solving the n by n set of equations, this time you solve more. In fact, as many more as you have constraints. So this method in linear problems hasn't been as popular as the others, but apparently has some advantage in nonlinear problems, and you hear quite a bit about it in contact problems. Now let's look at several of the methods that are used to modify the equations of equilibrium. It's a bit of a shopping list, and I'm going to present them roughly in the order in which they're done chronologically within the finite element codes, but the ordering really doesn't matter. We're going to start out with multipoint constraints. Multipoint constraints are a linear homogeneous relation between two or more coordinates. And these might be really at different nodal points, but on the other hand, it might be two coordinates at the same node, such as I've shown in the example below. It's interesting that the standard form is homogeneous. That means with a zero right-hand side. However, this equation can be converted into non-homogeneous form by using perhaps a scalar variable here for one of the degrees of freedom and then constraining it to take a specified value. So you could build a constant into this. This factor Rj is a coefficient, and there will be such a weighting coefficient on every one of the degrees of freedom. A typical convention is to remove the first degree of freedom in this list in favor of the others. So because it is a single algebraic equation, you can use it to remove one degree of freedom. I'm going to show an example here where we might use just a single multipoint constraint. For instance, if you had an inclined plane as shown here, and a body that was constrained to slide up and down it on this little cart, this wheeled cart, then you'd find that your degrees of freedom must move in this prescribed way, where U21 would have to equal U22. To put it in the form above, you would write it as so, with a +1 coefficient on U21 and a -1 coefficient on U22, setting it to be 0. So you can see how you can force such a simple system into such an equation. The multipoint constraint relation, however, is more complicated than you might think at first. Some years back I had been using these, and then I discovered at a point that I really didn't understand what I was doing. And here's why. If you take a single example of a multipoint constraint, one equation involving several variables, let's suppose we take that previous one with U21 and U22, and then the force F21 and F22. You'll find that when you use that single relation, that the variable U21 will disappear from the variable list in typical codes and be replaced by other components. But what you have done really is presumed a value of one of these two displacements, and you haven't specified anything about the forces. So although it might be interesting to think you could get away with prescribing one equation and eliminating both the force and the displacement, there's something illogical about that, and that's what caught me. Well, the answer is that when you specify such a multipoint constraint between the degrees of freedom on this side of the equation, simultaneously and hidden to the user, within the finite element code is imposed a condition that the forces do not do any work. In other words, it's a workless constraint, or a holonomic constraint, as the dynamicists say. And that equation is shown here, namely that the displacement must be orthogonal to the force. So in our case, if the forces over here are in red and the displacements are in blue, we've already constrained the displacements to run along this axis. Then, as a separate condition, it's required that the forces be perpendicular. And that means you have a workless constraint force. That can be written out in vector form shown here. And that is done for the user without any comment in typical codes. And so be aware of that at some point, that in fact for every displacement constraint appearing as a multipoint constraint, there is a hidden force relation that makes the constraint workless. Let's now consider symmetries that can occur in physical systems. I think we're all aware that there are reflective planes in many vehicles. There are cases where you have rotational symmetry about an axis. So we'll consider these as a form of modification of the equations. Some of them lead to single point constraints, some of them lead to multi-point constraints. We'll start with the reflective symmetry shown here, which is for an aircraft with a vertical reflective plane through the fuselage. And this is a useful concept when one has a plane of reflective symmetry in geometry, material, and displacement boundary conditions. But you do not have to have symmetry in the loading. That can be general. Let's call it asymmetric loading. And the procedure is to break the problem into symmetric loading and anti-symmetric loading, and then sum the two results. So let's look at this wing with a set of symmetric loads on it and a separate set of anti-symmetric loads. The symmetric loads are those to the back, drag loads, and those are mirror images of each other and therefore symmetric. These rolling loads, one down and one up, appear in the opposite sense that a symmetric pair would, and so we call those anti-symmetric loads. You can always resolve a question of whether loads are symmetric or not by indeed doing a mental experiment of putting a mirror at this reflective plane and then imagining what the image of this reflected load in the right half would look like. If that corresponds with what is truly on the left half, then you have a symmetric case. If it's opposite, then you have the anti-symmetric case. If it's a combination, then you have to break your loads down further. Now the way that this is handled, this is a traditional sort of breakdown of a problem into a symmetric load and set of boundary conditions and an anti-symmetric load and set of boundary conditions. And then these two are added up to give the total solution. This might seem suspicious in as much as you're solving two physical problems with different boundary conditions, but these really aren't free boundary conditions. These are cut planes that are exposing what's happening in the interior of the body, and this process is anticipating what would happen over the complete wing were it completely symmetric and then were it completely anti-symmetric. So it is technically correct, of course. Another kind of symmetry is called rotational symmetry or cyclic symmetry, and this has to do with bodies that have symmetry about an axis. Here I show a body with two regions. You could use the cross-hatched red region to replicate the other region, but merely by rotating it about that center axis. Here's a three-segmented pinwheel that can likewise be swept out in that same way, and the segments are spaced 120 degrees apart. Here's a solid body that shows that this is really a three-dimensional concept. It turns out the axis must be straight, and again you can rotate this fundamental region in the other three positions and create the rest of the body. The interesting thing about this form of symmetry is that you only need to model the cross-hatched fundamental region. You get conditions at the cut edges that are governed by multipoint constraints. In other words, the displacements, say, at that point must be related to the ones over here when you use cylindrical coordinates. So cylindrical coordinates are an integral part of this theory. It's really kind of an elegant theory. It's in the Nastran codes and others by now. Richard McNeil did a lot of the development on this, and I find it a very fascinating field. It's not used a lot in practice because perhaps because of the lagging on the graphics packages, that often they can't represent the results on the fully assembled body when you get them. But as a technical way to reduce the size of a problem, it's really wonderful and will save you occasionally when you can't get your given problem on the computer size that you have available. There's also a kind of symmetry that's a combination of reflective and rotational symmetry. It's called dihedral symmetry. Here you have perhaps a cartridge chamber or a hydraulic pump, as I have helped model, and you have holes that are periodically spaced around the central axis. But there are reflective planes of symmetry throughout here. In fact, there are apparently 4 of them, and you can subdivide this body into even smaller segments, such as this cross-hatched one, which, if you first reflected it, would give the other part of this region, and then together, if you rotated that combined region around 4 times around the axis, you sweep out the whole body. So this is an interesting kind of symmetry. Translational symmetry, shown below, is basically a lattice type of symmetry where a pattern is repeated on straight lines. The example I'm showing here is basically a bandsaw blade that's cutting through a really thick log. As a result, we might postulate that it is getting the same loading on a number of teeth at the same spot, although my sketch will be a little bit shaky. And therefore, the engineer can postulate that if you isolate one segment of this blade, then whatever is happening at one node on the boundary to the right will have to be the same as what happens on the node at the same position on the left. And so you can make kind of a homemade symmetry from those arguments. You still have to remove what are called rigid body modes, which we'll discuss later. So just making sure that this thing works in a periodic way isn't the whole answer, and there's even further modification to be done. Axisymmetry is a kind of symmetry that's often seen in lathe pieces and other bodies of revolution. Again, you need a straight axis of revolution. The body is swept out then by rotation of one surface, such as shown here in the cross-hatched view. And it is possible to have skew in this. I've never done such a problem, but you can account for that. More often, though, people are dealing with bodies that are either shell-like surfaces of revolution or solids of one material. When we discuss the reflective plane, I mentioned how the engineer must create symmetric and anti-symmetric boundary conditions at that cut reflective plane. And that's an important enough topic to devote a section to here in our lecture. So we will look at those boundary conditions, and it's a solved problem and something that you can more or less tabulate the answers and have them forever, but you need to go through this once. I'll start out with what are called elasticity elements, and these are solid bodies that only have the translational degrees of freedom. If I show you such a body here that has been aligned in a way that there's a reflective vertical plane, and then I just by coincidence have shown symmetric loads on it, then the engineer would attempt to model half of that and put symmetric conditions on this cut reflective plane. Now, I've shown a model for the boundary conditions as a set of rollers, and that's not obvious at first, but it will turn out that the reflective plane has that kind of physical interpretation, as if it were a greased surface or a sliding surface on rollers like that. We'll discuss that in the next figure. We'll look at this body in the entirety to see if we can infer what the conditions at its center line or its reflected plane should be. Here I show symmetric loading on such a body, and the reflective plane would go through here. It's really through the plane formed by the 2 and 3 directions. First of all, we might say that because of this balance of forces horizontally, we wouldn't expect the body to move either right or left, and at the center line at that plane of symmetry we would expect the translation in the one direction to be 0. Secondly, if we look at say these vertical forces here, we would realize that they will not have the ability to act against each other at this center line. They're headed in the same direction and they don't oppose. Therefore, there shouldn't be any shear force F3 if we were to cut that body at that point. And lastly, you would get the same effect by looking down from above in the 2 direction and would come up with this 0 force condition. Now, when you want to find the anti-symmetric boundary conditions, by far the easiest thing to do is to just take the complement of the symmetric conditions. So for instance, instead of T1, the translation in the one direction being 0, we know that it's the force in the one direction that's 0. Instead of the forces in the 2 and 3, it's the translations in the 2 and 3. So it's a change, I would call this the complementary conditions that occurs. You can argue these with some difficulty. For instance, on the first one, if we try to argue from first principles, if this force were horizontal and this one were horizontal, the question is, and if you cut a plane, can they act against each other to cause some net force across that middle? And the answer is no, that they both act in the same direction. So that argument is comparable to the one that we used earlier for these vertical forces over here. But the going gets tougher, and when you get into what are called elasticity, what are called structural elements, which I'll get to next, then you find that that's a difficult task, and I would rather rely on the complement of the symmetric case. Let's now consider structural elements. These are the ones that can carry moments and will support angular motion as well as the translational motion. Here is a flat plate-like body that has a reflective plane through its center, the green plane. I show some asymmetric loads on it, and the question is, if we were to divide this problem into a symmetric and an anti-symmetric part, what would the boundary conditions be at the cut plane? Well, we've really already figured out the translational quantities, so the only new thing would be the rotational ones. Over here we also know these translational quantities, so we're in pretty good shape on that, but the moments and angles are what we don't know. Well, let's think about this. If we were to look at rotations about this degree of freedom 1, to have mirror image moments about that, you would have a moment about this axis in this direction, and on the back side a moment that would have to also go in that same direction, you see. And the question is then, at the center point, could you have internally one of these acting against the other? And the answer is no, that since they're in the same direction they can't support, or they won't cause any internal moment like that, and so the moment about axis 1 is 0. If we look at this body from the top view and consider symmetric bending, it should be of this nature, and we would realize that on the reflective plane there really shouldn't be any net rotation about a vertical axis there, and that would be the third direction, so the rotation about the 3 axis should be 0. Likewise, on a front view, if we would look at it, we would hope to see symmetric bending like this with 0 slope about the 2 axis. So we can rather quickly determine the symmetric conditions. And then the anti-symmetric conditions over here will be the complement, where there was a moment on the left, moment about 1, we'll say the rotation about 1 is 0 on the anti-symmetric case. And then where there were 2 rotations, there become 2 moments to be 0. I have a friend, Subhash Kelkar, who has a little rule of thumb on this, which some people might find helpful, and it is that the symmetric problem under elastic deformation, if the reflective plane were firmly attached to the wing, it would tend to stay in the same plane. And so all of these conditions tend to keep that reflective plane where it is. Although it can slide and rotate within its own plane, it cannot bend away from that initial plane. And whereas the anti-symmetric boundary conditions do that, in fact, they allow such moving away from the initial reflective plane. So that's an interesting alternate viewpoint. Let's change now and talk a little bit about rigid body modes. Rigid body modes are a unique phenomenon that happens in bodies where the body can translate or rotate without causing any strain energy. As a result, you might say the body is very weak under that kind of a displacement field because it can happen at will and typically with arbitrary amplitude. Now, unless this is handled, it tends to destroy a stress calculation because the stiffness matrix becomes singular. This means that the determinant is 0. And then you cannot do the solution process. There's a sub-case of this which can be handled. It's called inertia relief, and it is installed in the Nastran programs and probably others, where an unbalanced force on a structure can indeed be equilibrated by reversed effective acceleration forces, D'Alembert forces. That's a special capability. I would probably view that as an advanced topic. So for the average practitioner, rigid body modes are an evil to be overcome as soon as possible. Let's consider a body in 3 dimensions, such as an airplane. This airplane can undergo the rotational motion, such as roll, pitch, and yaw, and also can do translational motion, such as plunging up and down. So any 3-dimensional body embedded in a 3-dimensional space has that possibility. So you must consider those 6 rigid body modes. There are a lot of physical problems where the problem is initially envisioned as being captured in a reduced dimension space. We have names for those: 2-dimensional problems, axis symmetry, plane stress, plane strain, and line elements that are constrained to slide upon a line. A physical example would be this telephone that's constrained to slide on a desk. Now, when you do such a reduction of a problem at the outset, then the remaining number of rigid body modes is severely affected. For instance, a telephone to slide on the desk can only translate in 2 directions and can rotate about a vertical axis. So you do get 3 rigid body modes remaining in such a system. There's a minor refinement that if the receiver were to fall onto the table and skitter around, then it too could have rigid body modes. And depending on whether it were allowed to roll or tumble, it might have even as many as all 6 of the original rigid body modes for a body in 3-dimensional space. A more restricted case would be a dial phone where the spring in the dial mechanism had broken, and then you would get a rotary degree of freedom. That's called a mechanism, and we'll talk about that in a little bit. If a body is constrained to lie symmetrically about an axis, and if the loads are also symmetric about that axis, then you have the case of axis symmetry. This is a rather special case, and the reason is that any such finite element modeling such a body is really a ring element that extends around the axis of symmetry. And so that any motion of that element outward would create hoop stress. Likewise, any rotation of such a body, if we have this entire meshed ring body here, if it were to be rotated to any extent, you would then be causing the outer elements to go into hoop tension, the inner ones to go into hoop compression. So those are clearly not rigid body modes, neither the rotation of this cross-section nor the translation outward. The problem statement typically implies that this cross-section cannot rotate about the axis and removing further degrees of freedom. So if you do have a ring element, in many codes it is presumed then to only have the remaining degree of freedom of sliding along the axis, sort of like the ring on your finger could slide along your finger. That would be the only rigid body mode in several of the codes. The SAP series used to be that way, as I recall. Now, on the other hand, in some codes, if this ring element may be embedded in a fully 3-dimensional space and might be allowed to rotate and do some of these other actions. So I view the axisymmetric case is very special and very code dependent in terms of rigid body modes. Make sure you check out your element and see what its mobility is in a 3-dimensional space. I've tried to summarize some of this previous discussion in a little chart, and sometimes these are good for purposes of argument but are not airtight. In this case, certainly it's true that the 3-dimensional body in a 3-dimensional space will have 6 rigid body modes. So that one we can say is an airtight situation. When you come to 2 dimensions, then the question is, does the element lie in a plane or is it allowed to float in space? If it's called a plane stress element, it often infers that it is restricted to lie in a given plane, and then you would have perhaps only 3 rigid body modes remaining in your structure. On the other hand, other codes will call it a membrane element and will allow it to float in the 3-dimensional space, in which case such a membrane body would really have 6 rigid body modes remaining. So this one's a little more argumentative, likewise with plane strain. The SAP codes used to embed these in a 2-dimensional space such that they really only had 3 rigid body modes. Axisymmetry likewise is argumentative. What do you mean by the axisymmetric element? Is it a ring? Is it a ring that can really move freely in 3-dimensional space, or is it just a cross-section which is not allowed to move about the axis but only slide along it like the ring in your finger? And that's what I'm assuming here, is that this is a classical old-time axisymmetric concept. One-dimensional situations are not encountered much. You would have one-dimensional elements lying on a one-dimensional line, and there would only be a single rigid body mode in that case, which would be sliding along that same line. So I do talk here about how the codes vary widely and how these subcases are handled, and you must check out the individual elements. Let's have a little practice at removing rigid body modes. This is something the engineer must be aware of. It requires that you use single point constraints, typically as many as you have rigid body modes to be removed, and the engineer must figure what points on the body can be constrained in order to remove the rigid body modes without doing any additional constraint that would imply restraining the body unduly. Here's a picture of a blimp, and I'm going to consider 4 points on the blimp: the nose and the tail, which are solid fixtures, fittings, perhaps aluminum tie-down points. Then the gondola, that would be a sheet metal and sheet and stringer construction, and then a point out on the membrane envelope of the body. Well, if we want to remove rigid body modes, the easiest way is to find one node, such as number 2 on the gondola, and restrict all 6 degrees of freedom to be 0. That's easy. That will, in fact, knock out all of the rigid body modes. What you're doing then is basically holding the body at that point and holding it for observation purposes. Sometimes I say that this is a photographic thing where you want to be able to get a good picture of the body. Now let's take a more ambitious removal of rigid body modes by dealing with the front and the back through solid elements. Node 1 and node 3 are those fittings, and I'm only allowed to handle translations. And so if I do, I'm going to take the 3 translations at the nose, which are shown in this figure below, and then at the tail I'm only going to constrain the translations in the 2 and the 3 directions. Now, the 2 and the 3 directions are the ones that are vertical and horizontal out toward the viewer. So what we have now is a blimp that is pinned at the nose, and then the tail has been restrained to prevent pitching and yawing. But what we haven't restrained yet is rolling. In other words, spinning about the longitudinal axis. And to do that, we need to go somewhere else such that we can prevent that rolling motion. And if we just pick any point on the membrane surface and find one that can be constrained in the 2 direction, which is out of the page of the paper for us, then that will knock out that rolling degree of freedom. This could not lie on the horizontal center line of the body. It would have to be up off the center line so that you could get some implied moment from such a constraint if need be. Then a bad case that I show, in other words, a straw man for trying to deal with rigid body modes, is shown below here, and that's where I only pin the nose and the tail and don't bother to really look at it further. What would happen there is you would have indeed established pins at the nose and the tail, sort of universal joints that can't move in the three directions. But this would not prevent the rolling motion at all. So you've missed constraining the rolling motion. Furthermore, you've done something bad. You have not allowed the body to have any net stretch in the fore and aft direction. And that means that there can't be any straining or any internal or any substantial thrust in this direction internally, because you're grounding any possible loads that way, pressure loads or whatever. So this is bad. We have missed the restraint of one of the rigid body modes, and we have added a restraint which is unwanted on an elastic type of motion, namely stretching of the fuselage. We mentioned earlier the possibility that a portion of a structure could become loose in some sense and clatter around. These are called mechanisms, and the first example we gave was the receiver of a phone falling off on the desk. But this happens quite a bit. And sometimes there are physical mechanisms, sliders, pin joints, and so on that have some useful function. Sometimes it's merely a modeling error. Let me show you an example of a modeling error that I made one time. And oh yes, professors and consultants do occasionally, once in a great while, make an error. And if you're fortunate, you catch it, as I did. In fact, I guess you could say most finite element people get smarter and smarter by making errors, and when you make errors at 3 a.m. and you've got a job due the next morning, you tend to remember that. Well, this one didn't keep me up at night, but it was puzzling at first in any event. This is a load ramp which is built primarily of I-beams running across the bed with a metal grating on top. Now the grating is not primary structure, so I removed it. But the load on this is typically a forklift truck that runs up and down with 4 wheels. And so there's a load pattern on the bed of this particular ramp. And then the beams will carry that out to the sidewalls. The sidewalls are plates. They have caps at the top and bottom that stiffen them. But I did calculate the stresses on this, and later, about 2 weeks after delivering the results on stresses and sizing the body and showing how it was critical here and not critical there and so on, I looked by chance at the output and found that there were 10 to the 32nd radians of rotation about the beam axis. And I was appalled. It was clear that I had missed something, obviously. And what I found then, in retrospect, was that this beam member across the bay here, and there were several of them because you need to have load application points in the interior, but this beam-like structure through the center of the bed here, although it has stiffness in respect to torsion about its axis, it was being connected at the 2 ends to plates that have no drilling degree of freedom stiffness. In other words, the classical Kirchhoff-Love plate theory, if you have a plate, it has no stiffness in regard to this torsional or this twisting degree of freedom called a drilling degree of freedom. Therefore, the beam was free to spin about its own axis. Now, this is not the kind of a problem that's easy to see mathematically, because you don't get zeros on the main diagonal of the matrix or at any single degree of freedom going bad. Rather, you get this total body called a mechanism, which in my case, let's say, was consisting of 3 beam elements end to end. And it in total was free to spin. Well, I grounded those beam elements at one end or the other through just a grounding of that torsional degree of freedom, and constraining it to 0, in other words, and then redid the stress calculation and found that it didn't affect the results at all. So the code I was using was strong enough to overcome that singularity or near singularity with the amount of precision that it was solving. And I'm still a little mystified that it did so well. Most codes nowadays won't even allow a solution if you have a singularity on that order. Another problem where this comes up is when you join plates, beams, and shells to solids, because the solid itself will not provide any rotation. The last entry in our rogues gallery of bad things that can happen to you en route to a stress solution is the nodal singularity. And this is where you have your mesh developed and a number of nodes, and off here at some particular node you have not connected enough elements to restrain the degrees of freedom in all 6 directions. In other words, there might be one direction which has no element restraining it. That becomes singular then, and it's called a nodal singularity or a grid point singularity. This one, in fact, can be sniffed out by logic and by analysis, because the computer code can concentrate on the stiffness for that single node and can do an eigenvalue problem and check the translational stiffness and then the rotational stiffness and develop the principal directions of stiffness and find the weakest one and find if it's 0. If it is, then that degree of freedom is bad. There would be in the Nastran codes, for instance, the process called the automatic single point constraint feature, and it's a parameter that's set, the auto SPC, that will faithfully look through your entire list of nodes and find out which degrees of freedom are singular for you and then print out a table. It will also fix that up for you and allow a run. Sometimes this is useful in training cases because it gets a run even if it's a fictitious body you have just studied. I know some of my professional friends feel that it's a little dangerous to use the auto SPC because it might fix up and then hide a problem in the model. But that's something that's well worth the risk in many cases. Certainly you should look at the constraint list that's been invoked then by your automatic searching out of those bad directions and then try to fix that if it's a modeling error. Let's do some problems now, and our first problem is going to be a body that we'd like to stress analyze, but it has a rigid body mode present. Let's look at the elastic deflection of this particular beam structure that is guided between 2 rigid walls. This means that the ends here, captured by plates, slide freely up and down, and there is therefore that rigid body mode possible. Yet the live loads are in equilibrium and form a well-posed problem where presumably this structure is going to bow in the middle in such a way. The body is symmetric, so it's possible to exploit the symmetry here also. And between the two then, between the outright removal of rigid body modes or the use of symmetry, we want to make sure that we have a well-posed problem when we finish. And the question would be then, how would you set this problem up? The logic of our solution is that we'd like to remove that rigid body mode so that it doesn't affect the elastic solution. Also, if possible, let's exploit the plane of reflective symmetry and solve only half the problem. Those two ideas couple together then in this figure shown here, where we see the 4 relevant degrees of freedom of the left-hand side of the body. Now, interestingly, we need to specify either the force-like or the displacement-like quantity in each of the coordinates. Because there is guided condition at the left end, we know that U2 is 0. And because there's a reflective plane at the center of the body, we know that U4 is 0. Then we have kind of a shearing situation where the body is going to be sheared by the live loads, which act at the left end and at the center. At this point, we can remove the rigid body mode in sort of an arbitrary way. We could either fix the vertical displacement at the left end or the right end, and arbitrarily I'm going to set the translation U3 to be 0. Okay, so I'm going to remove the rigid body mode by holding the beam fixed in our view at the center and allowing the left end to move upward. Let's combine those arguments about the displacements in this set of equilibrium equations. The sliding support on the left end enforces 0 rotation there. The symmetry condition at the center of the beam enforces 0 rotation here. And then our arbitrary removal of the rigid body mode by constraining the center of the beam in translation goes here. We've allowed the left end to be the live loaded end with this live load here. We don't know the moments that are required to hold the 0 slopes at the left and center of the beam. And at the cut plane, reflective plane, we know the live load there, but we don't know the interior shear force, which is then released by cutting it. And so we don't know the total reaction there. All told, we have 4 equations and 4 unknowns, but only one of the displacements is unknown, so that uncouples nicely. And we can solve directly then for the displacement U1 as the live load of 2,000 and divided by this stiffness, this EI 12 over length cubed. And solving for that, we get 0.0167 millimeters up. So the body does move upward at the left end, and as measured relative to our initial coordinate system lined up with the undeflected body on its axis. Our second problem will be one involving a reflective plane and then inferring some stiffness terms in the matrix for a single element. Here I show a hypothetical kite-shaped finite element with 4 nodes, and the reflective plane passes through the nodes 1 and 3 on the x-axis. I propose an experiment where we constrain the left 3 nodes, 1, 2, and 4, and then load the right node with this 200 Newton force at 45 degrees, and then we find that these are the resulting displacements. Now notice that they are not the same. In other words, this system is not symmetric in regard to stiffness in the horizontal and the vertical direction at this point, and that's what you'd expect. You'd expect it to be somewhat stiffer in the horizontal direction and therefore have a smaller displacement because you're on axis, if you think of terms of beam theory, whereas the vertical displacement is more involves something like a bending motion. So the question is, find as many of the stiffness terms as you can. Now the solution will involve setting up the equilibrium equations for this experiment that was discussed. We really have an 8 by 8 matrix here, so this is not a small matrix, and we wonder how many of these terms we might be able to find. The experiment per se, though, would say that we clamp the grid points shown here, and this one, and this one. And so we're imposing these displacements, 1 and 2, according to these loads over here. This is really sort of an what would you call it, a synthesis. We're really backing out of the results that we have what the system properties are. And in question are then these 4 stiffness terms. Now, of course, the off-diagonal terms must be equal, so that cuts it to 3 stiffness terms involved in this set of 2 equations. So we do have here then, directly from our equilibrium, 2 equations and 3 unknowns. And the question is all lost, or can we still use some of the information about the symmetry of the system? So we can back off at this point and do some arguments about the symmetry of the problem and see if that will allow some simplification. Let's consider a mental experiment similar to what we've done in our lecture. If this are a reflective symmetric plane on this axis, and then we modeled half the problem, we know that loads upon the on this body that are symmetric should cause symmetric boundary conditions on this cut plane. Among those would be then that there should be no vertical displacement here, U6, corresponding to such a symmetric live load F5. It's true in this case that the live load may be hard to figure as a symmetric load, but it is, even though it's on the reflective plane. So when we set up an equation for such a situation, we would have this set of equations below, and we're mostly interested then in the what would be the 6th equation. It would say K56 times U5 plus K66 times 0 equals 0, and that immediately gives the result in the next figure. So I'll write that result down immediately. And that's helpful to us because in our given physical experiment we had 2 coupled equations, and apparently at that time had 3 unknowns, but now we're allowed to cancel out the coupling terms, which must be 0 by this reflective symmetry. And that allows us to find K55 and K66 at that point. Now we can make other symmetry arguments as that first one. For instance, if we were to apply a live load to the left end of the element, we shouldn't get any displacement in the 2 direction. That leads to this hope then that K12 and K21 are both 0. You can do the same in the coupled case where you load in the 1 direction here and in the x direction on degree of freedom or grid point 1, and then you shouldn't get any displacement here in the 6th coordinate direction, so that gives you the K16 and K61 to be 0. And then lastly, on the comparable thing, if we load the right side and then look at the displacement at the left, we get this last one. So we really have found, let's see, K56, K65, there's 4 there, and there's 2, 4, 6 more here. So it appears that we have found 10 stiffness components from that original physical load case, as well as our symmetry arguments. Problem 3 has to do with a children's playground device called a teeter-totter. Here you have a body that's pivoted at the middle. It's basically a beam-like body. There are 2 loads on it which correspond to a heavier child sitting at a shorter distance and a lighter child at a farther distance from the pivot. The children figure this out pretty fast, and so it's interesting that they understand static equilibrium. Then, of course, their whole goal is to balance in a way that with very small forces they can rotate this and jump up and down at will. Our question is, how can we turn this into a stress and displacement problem from this statement? Because you see, obviously there's a rigid body mode present, and the stiffness matrix, if not modified, would be singular, and you would fail in your solution. Well, below I show the solution where I'm going to use 3 beam elements for an exact solution. the solution would be exact because the Euler-Bernoulli beam element using a cubic shape function is exact when there are only n loads on it, and that's all we have at this point. If we subdivide appropriately with the child's position as a force, the central pivot, and the second child, we really don't need the outboard unloaded beam element at the right, but I'll put it in because we might be interested in displacements. In the theory, that should be at zero stress and is going along for the ride in all senses of the word. Our goal is to set up the equations of equilibrium for this system, and so we need to make an assumption now on removing the rigid body mode. My suggestion is to set the rotation at the pivot point to be 0. That lets the teeter-totter deflect about a position that's a horizontal position, a rather nice reference position. You could, in fact, however, have constrained any of the other free degrees of freedom to 0 in order to remove the rigid body mode. I find it a little better, though, to put the constraint on an unloaded degree of freedom so that you don't get into the worry about the constraint force that you've added and whether it has to also ground a live load. But it would be, in principle, possible to have constrained any one of a number of degrees of freedom. Now, our resulting equations look as below. It's an 8x8 matrix formed from the 3 different beam elements, which we've assembled here in these 4x4 matrices. So you get these outlined here. And of course 0 is on the outside. The pinned condition calls for 0 translation at this degree of freedom, and then our assumption on removing rigid body modes has led us to put a 0 in this location for the rotation. We're able to put the live loads on the system, the 2 live loads, and then we can solve for the reactions at the pin, namely the physical translation, and then F4 plays the role of the moment of constraint there. We'll treat it as if it's unknown and solve for it, and then hope that it comes out to be 0. We wouldn't want our force of constraint in this case to remove the rigid body mode to have a finite value. We'd like it to be just like a kind of fairy fingers coming in and just softly centering that teeter-totter while the kids are in perfect balance on it. So that's our set of equations, which are then solved. Problem 4 is an exercise on looking at a system with a reflective plane and applying antisymmetric loads. Let's look at this bracket here made of 2 beams welded together, and it would be a frame in the civil engineering sense. This load applied at the junction is vertical. The reflective plane of symmetry of geometry, materials, and boundary conditions passes through this x-axis and is through the joint. So what we need to learn is how to handle the boundary conditions at this reflective plane, how to handle the load, how you recover the results in the image half of the solution that's not modeled. First of all, in the solution, you would recognize that this is an antisymmetric load, and that's not really trivial. For bodies that are loaded on the reflective plane, sometimes it's better to break it into 2 halves and split it between the real and the virtual image or the mirror image. If we did that, we'd have a half load up here and a half load here, and then you can see that those are not legitimate mirror images. In fact, they're the opposite of what you'd expect. So it's a pure antisymmetric load. It's not a general load. And we'll assume that we're going to solve the problem in the plane, in the XY plane, so we're not worried about out-of-plane bending. The boundary conditions on the cut edge there, where we apply the reflective plane, can be found by arguments similar to what we did in the lecture, and you may need to review that. They include these 6 conditions. Now, when you apply a live load at that same point, it complicates things a bit, because rather than a force to be 0 in the direction, let's say U5, the boundary conditions per se are saying that the interior force is 0. So rather than really using this one that says F5 equals 0, we're going to replace that with the one that says that that cut edge is loaded by an external live load of minus script F over 2. The minus because this is a downward load. Here you notice that I've got the real image on top and the mirror or the virtual image below, which we do not worry about. The displacement boundary condition at that cut edge is that there's no displacement horizontally. That's because, as in the general anti-symmetric case, that were there a load to the right above, there would have to be one to the left below, and then the presumption is that a point caught on the halfway between could neither move right nor left. The last idea we're interested in is how you might recover forces, displacements, stresses in the mirror image. And to do that, there really are 2 ways to look at it. They're equivalent ultimately. One would be to look at the image half as if it were in fact reflected onto the real half that you've studied, and then just change the signs on all of the quantities. You can interpret everything in terms of a right-handed coordinate system that way. Then somehow you're going to have to, in your mind, reflect that body back onto its true virtual image behind the reflective plane. But it lets you use a right-handed coordinate system. The other process would be to look at the body, the image body, in the position where it really is, and use left-handed coordinate systems there, and then take the results from the real solution and change the signs on them. Either way, you're forced to either reflect, you reflect the body one way or the other. But I have a suspicion that most people would prefer to do the first process of just imagine that lower half of the body reflected on the upper half, and then just change signs on everything. And that way you can continue to use a right-handed coordinate system. Now, as you can see, some of you are probably a little fuzzy about now reaching for your coffee cup or worse, and a shot of whiskey after that one. You might say that's a lot of trouble, and it turns out it is. Also, graphics packages often are not helpful in showing a reflected image, nor the cyclic symmetry problems that are theoretically possible. So, in fact, the practicing engineers nowadays will often solve the whole problem and let the graphics package then present you with the stresses in the other half of the problem in a very direct way, with no without use of left-handed coordinate systems or any such artifice. You just don't exploit the reflective plane. I think for someone who only uses this reflective plane idea once in a great while, maybe it is better to not take the risk. But if you're in a technology that has reflected planes and they're really important, then you'd better think about organizing and exploiting the reflective plane and only using half of the body. Okay, that finishes our problem session.